Take a breath. Let everything around you grow still. Whatever is pressing on your mind right now, set it down, just for a moment. You don't need it here, because right now, we are going to go somewhere very few minds have dared to follow. Not to a country you've never visited, not to an ocean depth you've never dived. We are going somewhere so far, so profoundly distant, that the word far no longer means what you think it means. We are going to the edge. Not the edge of a cliff, not the edge of a map. We are going to the edge of everything that has ever been seen, detected, measured, or imagined by human beings. The boundary where the observable universe simply stops. And then we are going to ask what comes after. Right now, as you listen to these words, you exist at the center of a sphere. This is not a metaphor. You are, in the most literal and scientific sense, standing at the exact center of your own observable universe. Every photon of light that has ever reached your eyes, every radio wave that has ever been caught by a telescope, every galaxy that has ever been mapped and named and cataloged, all of it sits within this sphere, with you at its heart. The boundary of this sphere lies approximately 46 billion light years away in every direction. Think about that for a moment. Not 46 million, not 46 billion light years. 1 light year alone is roughly 5.88 trillion miles, a distance so enormous that if you drove a car at highway speed without stopping, it would take you about 70,000 years to complete it. Now multiply that by 5.88 trillion. Now multiply that by 46 billion. Language was not built for numbers like these. And yet, every single thing humanity has ever studied, every star we have ever named, every nebula we've ever painted with our telescopes, every galaxy cluster stretching hundreds of millions of light years across, all of it fits inside this sphere. All of our science, all of our wonder, all of our cosmic maps contained. But that sphere has a wall, and beyond that wall, something exists. We just don't know what. Here is where the mystery begins. Here is where science, with all its instruments and equations and brilliant minds, looks out toward the horizon and finds not an answer, but a silence. A vast, impenetrable, almost philosophical silence. That silence is what we're going to explore tonight, because here is the thing that keeps cosmologists awake, not the fear of what might be out there, but something far more unsettling, the growing suspicion that what lies beyond our cosmic horizon might be more, much more, perhaps infinitely more. Perhaps structured and strange in ways that no human mind has yet had the language to describe. What if beyond the observable universe, there are regions so remote that light from them will never, in the entire remaining lifetime of the cosmos, reach us? What if the universe extends not for billions of light years, but for trillions, quadrillions? What if it never ends at all? What if somewhere, beyond the furthest wall of what we can see, there are other versions of everything, other galaxies, other stars, other worlds, and perhaps, in the most breathtaking possibility of all, other arrangements of matter so similar to our own that they produce other yous, These are not science fiction questions. These are the actual, serious, peer-reviewed questions being asked right now by the most rigorous cosmologists on Earth. And tonight, together, calmly, with open minds, we are going to follow them as far as thought can carry us. So settle in. The journey is long, and the distances involved are beyond what any human body could survive. But you don't need your body for this. You only need your curiosity. Close your eyes if you'd like. Imagine yourself floating, weightless, silent, suspended in the dark. Above you, below you, in every direction, stars, galaxies, the slow, ancient light of a cosmos 13.8 billion years old. You are small, impossibly, gloriously small, and yet you are here, awake, aware, a mind contemplating its own universe. That, in itself, is one of the greatest mysteries of all. But right now, there is an even bigger one waiting for us, just beyond the edge of everything we've ever seen. Let's go find it. Before we go further, let's make you a promise. By the time this journey ends, you will never look at the night sky the same way again. Not because you'll have learned a set of facts, but because you'll carry with you a feeling that is part wonder, part vertigo, part calm. The feeling that humans get when they stand at the edge of something truly, incomprehensibly large. Tonight, we are going to explore what might lie beyond the edge of everything observable. And that phrase, observable universe, is worth pausing on, because it contains within it one of the most important and least discussed ideas in all of science. The observable universe is not the whole universe. It is only the part we can see. This distinction sounds simple. It is actually one of the most profound statements in modern cosmology. Think of it this way. Imagine you are standing in a field at night, in total darkness, holding a single candle. The light from that candle illuminates a small circle around you. Everything within that circle you can see. Everything beyond the circle's edge exists, but you cannot see it, and you have no way of knowing what's there. Now imagine that the candle was lit exactly 13.8 billion years ago, at the moment of the Big Bang, and has been burning ever since, its light traveling outward in all directions at the speed of light. The edge of the circle of illuminated space is the boundary of the observable universe. Beyond it, light simply hasn't had time to reach us yet. But the field might go on forever. This is the situation we find ourselves in. We live inside a lit circle in an unlit field of unknown and possibly infinite size. And here is what makes this mystery special, what makes it different from other cosmic puzzles. This is not a mystery that better telescopes will eventually solve. The James Webb Space Telescope, breathtaking as it is, cannot see past the observable horizon. No telescope ever built or ever buildable with any technology we can imagine will pierce that veil. The information simply isn't there. The light hasn't arrived. It may never arrive. We are, in the most fundamental sense, cosmically isolated from much of what might exist. This is a boundary built not from ignorance but from physics itself. And yet, Science has found ways to reason about what might lie beyond it, not through direct observation, but through mathematics, through the careful extrapolation of what we can see. And what those tools suggest is extraordinary. Tonight, we will explore the leading theories. We will travel through the concept of the inflationary universe, a cosmos that expanded so rapidly after the Big Bang that regions of space-time were hurled beyond any possibility of contact. We will explore the possibility that space simply continues, flat and vast, stretching to distances so large that the word large loses all meaning. We will explore the multiverse, not as a science fiction concept, but as a serious mathematical consequence of the physics that governs our own universe. We will ask what it would mean if space is truly infinite. We will sit with that question gently, without rushing, because it deserves more than a quick answer. An infinite universe means, with a certainty that is mathematically inescapable, that somewhere out there, every possible arrangement of matter exists, every history, every outcome, every world. We will also explore the quieter mysteries, why our universe has the particular shape it does, why the numbers that govern physics seem so carefully chosen, and what that might tell us about whatever process gave rise to everything we know. These are not idle questions. They are at the very frontier of human knowledge, being debated by serious scientists at the most prestigious institutions on Earth. And they are among the most beautiful questions ever asked. So here is what we're going to do tonight. We're going to take this one step at a time. No rush. No pressure. We're simply going to think together about the most expansive, the most serene, and the most humbling idea in all of science. What lies beyond the observable universe? The question itself is a kind of gift. Let's unwrap it slowly. Every journey needs a starting point. Ours begins with a wall, not a wall you could touch, or see, or orbit around. A wall made of time itself. A wall that exists because the universe has an age, and light has a speed. And these two facts together create a boundary as real and absolute as any physical barrier in nature. We call it the cosmic horizon. And to understand what lies beyond it, we first have to understand exactly what it is. Imagine for a moment the beginning. Approximately 13.8 billion years ago, in an event we call the Big Bang, everything that exists, all matter, all energy, all space, all time, emerged from a state of almost incomprehensible density and temperature. The universe was not born into space. Space itself came into being. It expanded, cooled, and over billions of years gave rise to atoms, then stars, then galaxies, then, eventually, the quiet, dark night sky above your head. From the very first moment of that expansion, light began traveling. Photons were born and sent outward in every direction, moving at 186,000 miles per second, the fastest speed that physics permits. Those photons are still traveling today. But here is the key. Light can only have traveled a certain distance in 13.8 billion years, even at its extraordinary speed. Even across the vast gulf of cosmic time, light is limited. It cannot be everywhere at once. It cannot have crossed distances that simply required more time than the universe has existed. So the observable universe, the sphere of space from which light has had time to reach us, has a boundary, a horizon. And beyond that horizon, there may be galaxies, stars, and worlds that are just as real as our own, but whose light has not yet reached us and may never reach us. But wait, here is where the story already becomes more complex than you might expect. If the universe is 13.8 billion years old, you might assume the observable universe is 13.8 billion light years in radius. After all, that's how far light could travel in that time. But scientists tell us the observable universe extends approximately 46 billion light years in every direction. That's more than 3 times the distance light could have traveled. How is that possible? The answer is something both beautiful and strange. Space itself expands. The galaxies at the edge of the observable universe are not racing away from us through space like bullets through air. Space itself, the fabric of reality, is stretching. It is as if every point in the universe is moving away from every other point, not because anything is moving through space, but because space is growing between everything, like raisins in a rising loaf of bread. This means that by the time the light from a distant galaxy reached us, after traveling for billions of years, the galaxy itself had already moved much farther away, carried by the expansion of space. The galaxy we observe was once much closer to us than it appears. And this expansion has a deeply unsettling implication. The expansion of the universe is not slowing down. It is accelerating. In 1998, 2 independent teams of astronomers studying distant supernovae discovered something that overturned the expectations of an entire field. The universe is not just expanding, it is expanding faster with every passing moment. Something, we call it dark energy, though we have almost no idea what it actually is driving the cosmic fabric to stretch ever more rapidly. What this means for the future is stark. Galaxies that are today at the very edge of our observable universe, barely visible to our most powerful telescopes, will eventually be moving away from us faster than the speed of light. Not because they themselves exceed that speed, but because the space between us will be expanding so rapidly that the gap grows faster than light can cross it. At that point, those galaxies will cross our cosmic horizon and vanish. Not destroyed, not dead, simply unreachable. Gone beyond the boundary of what will ever again be observable from our location. And then another boundary will move, and another. In the far future, trillions of years from now, an observer in our galaxy will look out at the night sky and see almost nothing. The great clusters of galaxies that dominate our view today will have retreated beyond the horizon. The universe will appear, to that future observer, almost empty, lonely, as if nothing of significance existed beyond their own small cluster of stars. They will have no way of knowing, from observation alone, what we know today, that the universe is vast and rich and filled with billions of galaxies. That knowledge will have been swallowed by the expanding horizon. We exist in a privileged moment in cosmic history. The universe is young enough that we can still see the evidence of its origins. Old enough that structure has formed and the cosmos has become rich with complexity. But not so old that the great cosmic recession has hidden everything from view. We exist in a window, and beyond that window, something waits. Here is where the mystery deepens in a way that scientists find genuinely unsettling. We can observe up to the cosmic horizon, but the horizon is not the edge of the universe. It is merely the edge of what is observable from our location. There is no reason to believe, and every mathematical reason to doubt, that the universe ends at this boundary. Think again of that dark field with the candle. The edge of the light is not the edge of the field. It is only the edge of the light. So the question becomes, how much field is out there? And the answer that modern cosmology is increasingly confident in is a great deal more than you can possibly imagine. Some of the earliest and most important evidence for this comes from the shape of the universe itself. When scientists map the cosmic microwave background, the faint afterglow of light left over from the early universe, they measure it for signs of curvature. A universe with positive curvature wraps back on itself, like the surface of a sphere. A universe with negative curvature opens outward like a saddle. A flat universe extends in perfectly straight lines in all directions, forever. The measurements are clear. Our universe is flat, or at the very minimum, so close to flat that any curvature is unmeasurably small. And a flat universe, as mathematics tells us, must be either infinite or so unimaginably large that the difference is practically irrelevant. The part we can see, the 46 billion light-year sphere, is a speck within it. But that wasn't the strangest part, because when scientists began to think carefully about what drove the universe to be so flat, so large, so uniform in temperature across regions that seemingly could never have been in contact with each other, they arrived at a theory that would change everything we thought we knew about the scale of the cosmos. They called it inflation, and what inflation implies about what lies beyond our horizon is so vast, so extraordinary, that it will take us a moment to prepare ourselves before we can fully receive it. Let us go there next. There is a problem in cosmology so elegant and so mysterious that it has its own name, the horizon problem. Here is the puzzle. When we look at the cosmic microwave background, that faint afterglow of radiation left over from the early universe, often called the oldest light we can observe, we find something remarkable. It is almost perfectly uniform, from one side of the sky to the other, from regions 90 billion light-years apart. The temperature of this ancient radiation is the same to within 1 part in 100,000. Not approximately the same, almost exactly the same. And this is deeply, profoundly strange. In physics, when two regions of space reach the same temperature, it means they were in thermal contact. They were close enough to exchange energy and reach equilibrium, like 2 cups of tea that sat next to each other until they cooled to the same temperature. But the regions of the universe we're talking about, regions on opposite sides of the sky, have never been in contact, not in the entire history of the universe. The distance between them is so vast that even light, even in 13.8 billion years, has never bridged the gap. These regions have been causally disconnected since the very beginning. So how do they have the same temperature? For decades, this question sat at the center of cosmology like a splinter that couldn't be removed. And then, in 1980, a young physicist named Alan Guth proposed an answer so audacious that it seemed, at first, almost too convenient to be real. What if, in the first tiny fraction of a second after the Big Bang, we are talking about an interval of time so short it makes a millisecond feel like an eternity? Something in the range of 10 to the power of negative 36 seconds, the universe underwent a period of explosive, unimaginable expansion. Not the gradual expansion we observe today. Something almost instantaneous. Something that, in a sliver of time shorter than any clock could measure, took a region of space smaller than a proton and stretched it to a size larger than a galaxy. Then larger still, growing at a rate that, for a brief cosmic instant, exceeded the speed of light. Not because anything moved faster than light, nothing did, nothing can, but because space itself expanded at that rate. The fabric of reality inflated like a balloon, being filled by a force beyond our current understanding. This is inflation. And it solved the horizon problem beautifully. If the entire observable universe was, before inflation, a single tiny region smaller than an atomic nucleus, all in perfect thermal contact, all at the same temperature, then inflation simply stretched that region outward to vast size. The uniformity was there already. Inflation just scaled it up. It also explained why the universe is so flat. Just as a small patch on the surface of a vastly inflated balloon appears flat, even if the balloon itself has a slight curvature. Inflation would have smoothed away any initial curvature in the geometry of space, and it explained the faint ripples of temperature variation in the cosmic microwave background, the seeds of all future structure, as quantum fluctuations in the original tiny region, magnified to cosmic scale by the inflationary expansion. Inflation, in other words, is one of the most powerful and well-supported ideas in modern cosmology. But here is what it means for our journey tonight. If inflation is real, and the evidence strongly suggests it is, then the universe is not just larger than the observable sphere, it is almost incomprehensibly larger. Consider what happens during inflation. In that brief moment of exponential expansion, space grows by a factor of, at least, 10 to the power of 26, possibly much more. Current models suggest the actual expansion factor could be 10 to the power of 60, or perhaps indefinitely large, depending on the specific inflationary model. The observable universe, our precious 46 billion light-year sphere, represents what inflated from an original region far, far smaller than the whole. The entire observable cosmos is just one tiny patch of the post-inflationary universe. The rest, still there, still stretching outward, beyond the horizon, unreachable. A territory so vast that if you represented the observable universe as a single grain of sand, the total post-inflationary universe would be larger than any number we have a name for. Yet another mystery emerged from inflation, and it is one that scientists find deeply unsettling and deeply exciting. Most inflationary models do not produce a universe that stops inflating cleanly. Instead, they produce what theorists call eternal inflation. The idea is this: inflation is driven by a field, a kind of energy embedded in space that decays over time, ending the inflationary phase and giving rise to the hot, matter-filled universe we inhabit. But in many models, quantum fluctuations mean that in some regions of space, inflation never stops. Those regions keep expanding, producing new space faster than inflation can end within them. Think of it like a foam, bubbles of non-inflating space. Universes like ours pop into existence within an eternally inflating background. Each bubble is isolated from the others by the unceasing expansion between them. Each bubble is, to its inhabitants, the entire universe, because the space between bubbles is growing so rapidly that no signal from one can ever reach another. We may be inside one such bubble. Our Big Bang may have been the moment our bubble stopped inflating. And beyond our cosmic horizon, beyond the furthest galaxies we can detect, the inflationary background may still be churning, still expanding, still giving birth to other bubbles, other universes, with no end in sight. The answer raised an even bigger question. If this is true, what are those other bubbles like? And this is where things become even more fascinating. Because inflation doesn't just produce other universes. It produces universes that may be fundamentally different from our own, with different physics, different constants, different rules. Universes where gravity is stronger or weaker, where atoms cannot form, where stars burn out in seconds or last for trillions of years, where the forces that bind matter together simply don't exist. We are used to thinking of the laws of physics as universal, fixed, inevitable, but inflation suggests they may be local, specific to our bubble, an accident of the particular way our region of the inflationary foam came to rest. This is one of the most profound and most controversial ideas in modern physics. Not everyone accepts it, but it is a serious scientific possibility, the logical consequence of following the mathematics of inflation, wherever it leads. And it leads somewhere extraordinary. It leads to the idea that beyond our observable universe, beyond the wall of light, beyond even the post-inflationary cosmos, there may be a landscape of universes, a multiverse, so varied and so vast that ours is just one note in an orchestra too large for any mind to comprehend. But we haven't yet asked the simplest version of the question. Before the bubbles, before the eternal inflation, before any of these grand cosmological structures, what if space is just flat and vast, extending uniformly in all directions, without any exotic structure at all? What would that mean? That question, perhaps the most quietly mind-bending of all, is where we're going next. Let us set aside for a moment the drama of inflation and multiverses. Let us ask a simpler question. What if the universe is just big? Not exotic, not bubbling, not divided into separate regions with different laws. Just space, ordinary space, continuing outward from our observable sphere in all directions, flat and uniform, following the same laws we know, containing the same kinds of galaxies, and stars and matter we observe here? What if it simply goes on? This is perhaps the most scientifically mainstream possibility. Many cosmologists believe the universe is genuinely infinite, or so vast in size that the distinction between very large and infinite has no practical meaning. And if that's true, something follows from it that is so strange, so quietly astonishing, that most people who encounter it need to sit with it for a moment before it settles in. If the universe is infinite, then every possible arrangement of matter must exist somewhere. Not might exist, must exist. Here is why. The number of possible arrangements of the particles in any given region of space is enormous, but finite. Particles can only be arranged in so many ways. If space is infinite, if it contains infinitely many regions identical in size to our observable universe, then every possible arrangement must appear somewhere. Because there are more regions of space than there are possible arrangements to fill them. Think of it like an infinite library. The library contains every possible book, every possible arrangement of the 26 letters of the alphabet, across every possible page count. Most books are pure noise, random letters that mean nothing. But somewhere in that infinite library is a perfect copy of every book that has ever been written, every book that could ever be written, every story that will never be written. Now imagine the library is not books, but arrangements of matter, arrangements of atoms, of molecules, of particles. Somewhere in an infinite universe, there is a region of space that contains an arrangement of matter statistically identical to our observable universe, an identical Milky Way galaxy, an identical solar system, an identical planet Earth. And on that planet, an identical you. Not a copy made deliberately, not a twin, a statistical inevitability, an arrangement of matter so similar to the one that makes up your body, your brain, your memories, that there is no physical difference between you and it. Scientists who take this seriously, and some of the most respected cosmologists do, estimate that the nearest such statistical copy of our observable universe would be located at a distance of roughly 10 to the power of 10 to the power of 118 meters away, a number so large that it would require more space than exists on all the paper ever produced to write it out in full. Yet, in a truly infinite universe, that distance means nothing. Infinity contains it and goes beyond it without effort. What happened next surprised researchers, however, was not the statistical inevitability of copies. It was what this implied about identity and uniqueness. If you exist infinitely many times across an infinite universe, not metaphorically, but as a physical arrangement of matter, what does it mean to be you? What does uniqueness mean in an infinite cosmos? These are not questions with easy answers. They are questions that blur the boundary between physics and philosophy, but they arise naturally, inevitably, from taking seriously the possibility of an infinite universe. Scientists soon discovered that this concept, what physicist Max Tegmark calls the level I multiverse, doesn't require exotic physics. It requires only two things: a universe that is genuinely infinite or sufficiently large, and a universe with enough uniformity that the same physical laws apply throughout. Both of these conditions appear to be satisfied by our universe based on current observations. The observable universe shows no sign of edges in any direction. The laws of physics appear to be the same across all regions we can observe. The cosmic microwave background is uniform. The distribution of galaxies on the largest scales is the same everywhere. There is no observational evidence that our observable sphere is special. No sign that the universe grows thin or strange near its edge. It simply continues, as far as any of our instruments can detect, in the same pattern. This suggests strongly that whatever lies beyond the horizon looks much like what lies within it. The same vast stretches of intergalactic space, the same slow drift of galaxies, the same ancient light of aging stars, an ocean of sameness, which is, paradoxically, one of the most astonishing things in the cosmos. Because here is what that ocean contains. Not just copies of our observable universe, but all possible variations, universes where one quantum event went differently at the moment of your birth, where one choice was made differently, where one star formed in a slightly different orbit. All of these, every possible permutation, existing somewhere in the vast, quiet expanse beyond our horizon. Scientists soon discovered, however, a disturbing implication of this picture. If infinitely many versions of you exist, most of them are in situations statistically identical to yours. But a small fraction, infinitely many, because infinity has no small fraction, exist in situations radically different, in universes where, by random chance, the matter that surrounds them has arranged itself into improbable configurations, where impossible things have happened without supernatural cause. In an infinite universe, even the most improbable event is not just possible, it has already occurred infinitely many times. This unsettles some philosophers. It also unsettles some physicists, because it means that in an infinite universe, probability itself behaves in strange ways. The question, how likely is this to happen, loses its normal meaning when the answer is infinitely many times. Somewhere, the answer raised an even bigger question. Does this mean our universe is not special? Is the extraordinary precision of its physical constants, the exact values that allow atoms, stars, and life to exist, just one arrangement among infinitely many, with other arrangements producing sterile or short-lived universes? This question brings us to what may be the deepest mystery beyond the horizon. Not the geometry of space, but the question of why anything exists like us at all. But before we go there, we need to travel a little further. We need to look at the one observation that, more than any other, opened the door to all these visions of a larger cosmos. We need to travel to the very first light. There is a frequency of radio waves, barely distinguishable from the background hiss of any old electronic device, that permeates the universe in every direction. It is everywhere. It fills the sky. It passes through walls, through bodies, through the space between atoms. Right now, as you listen to these words, it is moving through you, ancient, faint, carrying a message from an era of the universe so remote that no object we can directly observe was yet in existence. We call it the cosmic microwave background. Scientists sometimes call it the CMB, or, with quiet reverence, the afterglow of the Big Bang. It is the oldest light in the universe, the light from the very first time the cosmos became transparent. Here is its story. For the first 380,000 years after the Big Bang, the universe was a hot, dense plasma, a fog of charged particles so thick that light could not travel through it. Photons were constantly absorbed and re-emitted, trapped in a churning sea of energy. The universe was opaque. Nothing could be seen. Nothing could escape. Then, slowly, the universe cooled enough for electrons to combine with protons and form neutral hydrogen atoms. The fog lifted. Light was free. And in that moment, 380,000 years after the beginning, the universe flashed into transparency, and a sea of light flooded outward in all directions. That light has been traveling ever since. Today, 13.8 billion years later, it has reached us. Stretched and cooled by the expansion of space, it no longer vibrates as visible light. It has been redshifted all the way down to microwave frequencies, cold as the void, barely above absolute zero. But it is there, measurable, mappable. Two engineers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were trying to eliminate an annoying background noise from their antenna. They checked every source they could think of. Loose connections, equipment malfunction, even pigeon droppings. Nothing removed the hiss. Eventually, they realized with growing astonishment that the noise wasn't coming from their equipment at all. It was coming from the sky, from every direction simultaneously, from the universe itself. They had accidentally discovered the cosmic microwave background. It earned them the Nobel Prize. But the full power of the CMB as a tool for understanding the cosmos and the mystery of what lies beyond the observable universe came later, when satellite missions mapped it in extraordinary detail. What happened next surprised researchers in profound and lasting ways. The map of the CMB is, in one sense, a map of the infant universe. Those faint variations in temperature, ripples of 100,000ths of a degree, represent the quantum fluctuations of the very early cosmos, inflated to macroscopic scales by the period of inflationary expansion. They are the seeds from which all future structure grew. Every galaxy cluster, every vast cosmic web of filaments and voids that we observe today, all of it traces back to those ancient ripples. But the CMB also reveals something about the overall shape and size of the universe. When scientists measure the angular size of the temperature fluctuations, how large the ripples appear on the sky, they find a pattern consistent with a flat universe. Not just approximately flat, precisely measurably flat within the limits of what current instruments can detect. And a flat universe, as we discussed, points strongly toward either an infinite cosmos or one so vast that the difference is academic. Yet another mystery emerged from the map. When cosmologists study the CMB in detail, they find hints of patterns, anomalies, that are difficult to explain within the standard model of cosmology. Large-scale alignments in the temperature distribution, an unusual suppression of fluctuations at the largest scales, a feature sometimes called the axis of evil, a preferred direction in the CMB that seems to align, puzzlingly, with the plane of our solar system. Most scientists believe these are statistical flukes, the kinds of apparent patterns that occur randomly in any limited sample. But a minority argue they could be signatures of something more exotic, the imprint of a region of space beyond our horizon that somehow influenced the early universe. If that sounds strange, consider this. During the inflationary epoch, regions of space that are now beyond our cosmic horizon were once close enough to be in contact. Whatever happened there could, in principle, have left a trace on the primordial plasma that gave rise to the CMB. In other words, the first light might carry whispers of a universe beyond our sight. Scientists soon discovered a related puzzle. The temperature pattern of the CMB appears to a high degree of precision, as if the universe began in a state of extraordinary uniformity. The initial conditions were almost perfectly smooth, with quantum fluctuations providing only the tiniest variations. This smoothness is extraordinary. In thermodynamics, smooth initial conditions represent low entropy, a highly ordered, improbable state. The early universe, by every measure we have, began in a state of remarkable order. Why? This is called the problem of initial conditions, and it is one of the deepest unsolved questions in physics. Most processes we observe move from order to disorder, from low entropy to high entropy. The universe, at its origin, was at its most orderly. What caused that? Some physicists argue that inflation naturally produces such initial conditions. Others suggest that the answer lies in what came before the Big Bang, if before even has meaning in a context where time itself may have begun. And some argue that in an infinite multiverse, our universe's smooth initial conditions are simply the result of selection. Only universes with the right conditions give rise to observers who can ask these questions. The answer raised an even bigger question. Is there anything at all beyond the cosmic horizon that we could, even in principle, detect? For a long time, the answer seemed simply to be no. But recent ideas in cosmology have suggested some extraordinary loopholes. One of them involves bubbles. If we live in a bubble universe, one of many produced by eternal inflation, then occasionally, with vanishingly small but non-zero probability, two bubble universes could collide. Such a collision, even a glancing one at the edge of the inflationary foam, would leave a distinctive imprint on the CMB, a circular ring of slightly higher or lower temperature. Cosmologists have searched for these rings. So far, none has been definitively confirmed. But the search continues, because if we ever found one, a circular scar on the CMB, left by the collision of our universe with another, it would be the first direct evidence that something exists beyond our cosmic horizon, the first message from beyond the edge of everything. And this is where things become even more fascinating, because it turns out that the question of what lies beyond the horizon is not just a question of scale. It is also a question of physics. Our universe runs on numbers. Not approximately, not loosely, but with a precision that is, when you examine it carefully, deeply, and almost disturbingly exact. The speed of light, the gravitational constant, the mass of the electron, the strength of the electromagnetic force, the cosmological constant, the energy of empty space that is driving the accelerating expansion of the universe. These numbers are not derived from deeper principles. They are, as far as current physics can tell, simply given, measured, recorded, used. Their values are what they are, and the cosmos that results from those values is the one we inhabit. But here is what makes these numbers so mysterious. They are extraordinary, not in a metaphorical sense, in a mathematical sense. If you changed the gravitational constant by a fraction of a percent, stars could not form. No stars means no heavy elements, no carbon, no oxygen, no iron. No heavy elements means no chemistry. No chemistry means no biology, no life, no minds, no questions. If you changed the mass of the electron relative to the proton by a small amount, atoms would not be stable. Chemistry, once again, would be impossible. If the cosmological constant, the energy of empty space, were even slightly larger than it is, the universe would have expanded so rapidly after the Big Bang that matter could never have clumped together. No galaxies, no stars, no worlds. Some physicists have calculated that if you could randomly choose the value of the cosmological constant from the range of values that seem physically possible, the probability of landing on a value that permits the formation of structure, and thus life, is something in the range of 1 in 10 to the power of 120. That is a probability so small that the human mind genuinely cannot process it in any intuitive way. And yet, here we are, in a universe with exactly the right values. This is known as the fine-tuning problem, and it is one of the most debated and most profound questions in modern physics and philosophy. Why do the constants have the values they have? Why are they so precisely suited for the existence of complex structures? 3 broad categories of answer have been proposed. Each has profound implications for what might lie beyond the observable universe. The first is, perhaps it's a coincidence. Perhaps the universe simply has these values, and we are here to notice it only because a universe with different values would not have produced us. This is the anthropic principle, and while it sounds circular, it has genuine explanatory power. Of course, we observe a universe compatible with our existence, because incompatible universes produce no observers. But many physicists find this unsatisfying. It doesn't explain why the universe has these values. It only notes that we are here to see them. The second answer is, perhaps there is a deeper theory that makes these values inevitable. Perhaps there is a framework, a more fundamental physics, from which the standard model emerges naturally, with no free parameters. String theory and its successors are attempts to find this framework. If it exists, the fine-tuning problem dissolves. The constants would be what they are because they couldn't be otherwise. But we don't have that theory yet. String theory, in its current form, doesn't uniquely predict the values of the constants. It predicts, instead, a landscape. And this is where the multiverse returns. The third answer is the most exotic and the most contentious. Perhaps the constants are different elsewhere. Perhaps, in the landscape of universes produced by eternal inflation, different regions of space, different bubble universes, have different values for the fundamental constants. The laws of physics in our universe are local, not universal. Our bubble happened to have the right values by chance. Other bubbles have different values, and in most of them, complexity never arose. We are here not because our universe was designed for us, but because of the same logic that explains why you exist on Earth and not on a lifeless asteroid. Given sufficiently many places, some of them will be suitable for life, and life will only ever find itself in the suitable ones. This is the anthropic selection argument applied to universes. Scientists soon discovered that this answer, while intellectually coherent, has a deeply troubling implication. It may be unfalsifiable. If other universes have different constants and are forever beyond our horizon, we cannot test this hypothesis directly. We can reason about it. We can look for its indirect signatures, but we cannot confirm it by observation. Some physicists argue this means it is not truly science, that a hypothesis which cannot, even in principle, be tested is a philosophical claim dressed in the language of physics. Others argue that falsifiability is too narrow a criterion for theories that deal with genuinely unobservable realms. Mathematics can be rigorous and meaningful even when its subject matter lies beyond direct empirical reach. This debate is alive and ongoing. It is one of the front lines of modern physics. But here is what it reveals about the mystery of what lies beyond the observable universe. Whatever is out there, whether it is more of the same, or eternal inflationary foam, or a landscape of radically different universes, it connects back to the deepest questions we have about our own existence. Why are the constants what they are? Why is there something rather than nothing? Why is the something that exists a cosmos capable of giving rise to minds that look outward and wonder? The answer raised an even bigger question, one that sits beneath all the others like a foundation stone. What is the universe made of at the deepest level that makes any of this possible? And one piece of that foundation, one piece that is both familiar and utterly mysterious, lies in the strange quantum nature of reality itself. Every object around you, every atom in the walls, every molecule in the air, every particle in your own body, obeys rules that are deeply, irreducibly strange. Not strange in the way that distant galaxies are strange, because they are far away and hard to visit. Strange in the way that the closer you look, the less the familiar rules apply. Strange in the way that the building blocks of everything, the quarks and electrons and photons, behave in a manner that no classical intuition can fully prepare you for. Welcome to quantum mechanics, and while it might seem at first like a detour from our journey beyond the observable universe, it is not, because the quantum nature of reality may be the most important key to understanding what lies beyond the horizon. Here is the heart of quantum strangeness. In the quantum world, particles do not have definite positions and definite velocities at the same time. They exist in what physicists call a superposition, a blend of many possible states simultaneously. When you observe them, when you measure them, the superposition collapses and one definite outcome emerges. But until that measurement, the particle is, in a very real physical sense, in multiple states at once. This is not a limitation of our instruments. It is not that the particle secretly has a definite position, and we just don't know it. The mathematics, and the experiments confirming that mathematics to extraordinary precision, make clear that the indefiniteness is real. The superposition is real. So what happens when a superposition resolves? When the quantum coin lands and the particle settles into one definite state? What happened to the other possibilities? In the most widely taught version of quantum mechanics, they simply vanish. The wave function collapses. One outcome becomes real, the others cease to be meaningful. But there is another interpretation, one that is increasingly taken seriously by physicists, one that has direct consequences for the question of what lies beyond our observable universe. It is called the many worlds interpretation, proposed by physicist Hugh Everett III in 1957, and its central claim is as simple as it is staggering. The wave function never collapses. Every time a quantum event occurs, every time a particle could go left or right, could spin up or spin down, could decay or not decay, the universe branches. Both outcomes happen. Both possibilities become real. The universe splits into two or more distinct branches, each experiencing a different outcome. In one branch, the particle went left. In another, it went right. You, right now, exist in one of these branches. But in every moment of your life, in every moment of every particle's interaction across the entire history of the universe, branches have been splitting. The number of branches by now is incomprehensibly large. Each is as real as every other. If the many worlds interpretation is correct, and it is mathematically consistent, and many physicists consider it the most elegant solution to the measurement problem, then what lies beyond our observable universe is not just more space, not just other bubble universes. It is also other branches, other histories, other versions of everything that has ever happened since the Big Bang. This is the level 3 multiverse in physicist Max Tegmark's classification. A branching multiverse, arising from quantum mechanics itself, rather than from inflation or geometry. What is remarkable is that these three different pictures, the infinite flat universe, the inflationary landscape, and the quantum branching, all point in the same direction, toward a cosmos vastly larger, vastly more complex, vastly more populated than the observable sphere we inhabit. They converge on a universe in which our observable reality is a small local region of an immensely larger whole. Yet scientists soon discovered something curious about the quantum world that bears directly on the nature of the cosmos at its largest scales. One of the strangest features of quantum mechanics is that it is not deterministic. The outcome of a quantum measurement is genuinely random. Not random in the sense that we don't know the cause, but random in the sense that no prior information, even in principle, could predict it. The universe, at its most fundamental level, is not a clockwork. It is a gambler. This randomness is not a bug. It is a feature. Without quantum fluctuations, the universe would be perfectly uniform. No density variations, No seeds of structure, no galaxies, no stars, no us. The random rolls of the quantum dice, amplified by inflation, produced the patterns in the cosmic microwave background, produced the large-scale structure of the universe, produced everything. And the randomness is ongoing. Right now, in this moment, countless quantum events are occurring throughout the observable universe, and, presumably, throughout whatever lies beyond, each one branching according to the many worlds view, each one contributing to the ever-expanding complexity of reality. The answer raised an even bigger question. If quantum randomness is the source of cosmic structure, then what determines the range of possibilities over which randomness can play? What determines the laws themselves? This question, what physicists call the problem of meta-laws, the laws that govern the laws, reaches toward the deepest mystery of all. Why is there a physical universe at all, rather than nothing? And it is here that we encounter one of the most extraordinary, most speculative, and most beautiful ideas in all of theoretical physics. The idea that everything mathematically consistent must exist. Imagine that mathematics is not a tool we invented to describe the world. Imagine that mathematics is the world, not metaphorically, not as a useful shorthand, but literally. The universe, at its most fundamental level, is a mathematical structure. Objects, forces, space, time, all of it is ultimately made of relationships, patterns, equations, not described by math, made of it. This is the mathematical universe hypothesis, proposed by physicist and cosmologist Max Tegmark. It is one of the most radical and most carefully argued ideas in modern theoretical physics. And if it is true, or even if it is half true, it has extraordinary implications for what lies beyond the observable universe. Here is the core of the argument. Science has always used mathematics to describe the physical world. This seems, at first, completely natural. Of course, we use math. It's a precise language. But physicists have long been puzzled by just how unreasonably effective mathematics is at describing physical reality. Equations developed for purely abstract mathematical reasons, with no reference to physical observation, turn out, years or decades later, to match experimental results to extraordinary precision. This happened with the mathematics of curved spaces, which later became the foundation of general relativity. It happened with the mathematics of group theory, which turned out to describe the symmetries of particle physics. It happens constantly. The mathematician Eugene Wigner called this the unreasonable effectiveness of mathematics in the natural sciences. The precision is not just useful, it is mysterious. Why should abstract mathematical structures, developed in the minds of mathematicians with no physical motivation, turn out to describe the universe? Tegmark's answer is simple and radical, because the universe is a mathematical structure, not described by one, it is one. The universe doesn't merely obey mathematical laws, it is mathematics. If this is true, then a natural question arises: which mathematical structure is our universe? And a natural follow-up: are there other mathematical structures? Mathematics contains infinitely many possible structures. Group theory, topology, number theory. Each branch opens into vast landscapes of abstract relationships. Most of these have no obvious physical interpretation. But if the universe is a mathematical structure, then any mathematical structure that is sufficiently consistent could, in principle, be a universe. And what lies beyond our observable universe in this framework is not just more space or other bubble universes with different physical constants. What lies beyond is other mathematics, other universes defined by different mathematical structures, different geometries of space-time, different numbers of dimensions, different relationships between energy and matter. Perhaps universes where cause and effect work differently. Universes where time has 2 dimensions instead of 1. Universes described by mathematical structures so alien that they bear no resemblance to anything we could picture. Yet, another mystery emerged from taking this idea seriously. If every mathematically consistent structure exists as a universe, then the question of why our universe has the physical laws it has becomes, in a sense, trivial. Our universe has these laws because these laws define this mathematical structure. Other mathematical structures have other laws. We exist in this one because it permits existence. But this raises the question of what existence even means in this context. If mathematical structures exist independently of any physical instantiation, if they are real, simply by virtue of being consistent, then existence and mathematical possibility become the same thing. This is metaphysics at the edge of physics. Most scientists would prefer not to go here, but following the logic honestly leads here, and some of the most rigorous thinkers in physics are willing to follow it. Scientists soon discovered, however, a practical challenge with the mathematical universe hypothesis. It is extraordinarily difficult to test. If all mathematical structures are equally real, what predictions does the theory make about our specific mathematical structure? How would we tell the mathematical universe hypothesis from an ordinary physical universe with weird coincidences? The honest answer is, we don't yet know. The hypothesis is more of a framework, a way of thinking about what reality fundamentally is, than a specific prediction machine. But it connects to something concrete and testable. If mathematical structures vary in their complexity and their information content, then the universe we observe should, if this framework is correct, be among those that are sufficiently complex to permit the emergence of structures capable of mathematical reasoning of minds. In other words, because simpler mathematical structures, by definition, don't contain such structures. This is another version of the anthropic principle, now applied not just to the values of physical constants, but to the choice of mathematical framework itself. And it leads, naturally, to one of the most peaceful and most vertiginous realizations that cosmology offers. The universe was not designed for us, but it contains us. And in containing us, in having the precise mathematical structure that gives rise to minds that can reflect on its nature, it has done something remarkable. It has become aware of itself. You, right now, are the universe looking back at itself, the mathematics contemplating the mathematics, the structure examining the structure. And this is where things become even more fascinating, because this realization doesn't shrink you. It doesn't reduce you to an insignificant accident in a vast and indifferent cosmos. It places you at the very center of the story, not the center of the universe spatially, not the center of importance cosmologically, but the center of a great loop of awareness in which matter, organized by the random quantum rolls of 13.8 billion years, has arranged itself into something that can ask, what lies beyond? That question is not separate from the universe. That question is the universe doing something extraordinary, something that, as far as we know, only happens in very special mathematical structures, very special arrangements of matter. The answer raised an even bigger question. Are we alone in this awareness, across the infinite space, or infinite branching, or infinite mathematical landscape beyond our horizon? Do other minds ask the same question? That question is where we go next. Somewhere, right now, another mind may be looking up. We don't know this. We cannot prove it. It may be the most important question in science, and we have as yet no definitive answer. But in a universe this large, or infinite, the question of whether consciousness exists beyond our horizon is not merely philosophical. It is statistical. It is logical. It is, in the most rigorous sense, a scientific question, even if it is one we currently lack the tools to answer. Let us think carefully about what we know. Life, as we understand it, requires chemistry. Chemistry requires atoms. Atoms require the specific conditions of stellar nucleosynthesis, the process by which stars forge heavy elements in their cores and scatter them across space in their depths. This process requires stars. Stars require the formation of galaxies. Galaxies require the gravitational collapse of matter from the initial density fluctuations. All of this requires a universe with the right physical constants, the right amount of time, and the right large-scale structure. Our universe has all of this. It has had it for billions of years. Beyond our observable sphere, in the vast, unmapped expanse of the flat, continuing universe, there is every reason to believe, based on the uniformity of the CMB and the apparent consistency of physical law across all observable regions, that the same conditions apply. The same kinds of stars form. The same kinds of supernovae scatter heavy elements. The same kinds of molecular clouds give rise, eventually, to planets. And on some fraction of those planets, under the right conditions, chemistry crosses a threshold into biology. That threshold, the origin of life, is one of the great unsolved problems in science. We do not know with confidence how life began on Earth. We do not know how common the conditions for life are. We do not know whether life, once begun, reliably evolves toward complexity, intelligence, and consciousness. But we know that it happened here, once, definitively, and in a universe containing something in the range of 2 trillion galaxies in the observable sphere alone, each containing hundreds of billions of stars, each with a probability of hosting planets, some fraction of which may host chemistry similar to Earth's. The raw numbers are vast. If the probability of life arising on any given suitable planet is even vanishingly small, the expected number of life-bearing worlds in the observable universe is still large. Now extend this beyond the horizon. in a cosmos containing billions of times more matter than the observable sphere, or infinitely more if the universe is infinite. The number of potential life-bearing worlds scales accordingly. What happened next surprised researchers in the field of astrobiology. Rather than finding simple answers, the more carefully the question was studied, the more deeply it opened. Because the question of consciousness beyond the horizon is not merely a question of whether other minds exist. It is a question of what kinds of minds. The universe has been around for 13.8 billion years. Life on Earth has been complex for only about 600 million years. Technological civilization has existed for perhaps 10,000 years. Modern science, capable of asking questions about the nature of the cosmos, for only a few centuries. In the full timeline of the universe, we are extraordinarily young. If any civilization reached technological sophistication, even a million years before us, a timescale that is 1/100th of 1% of the age of the universe, they would have had a million additional years to develop, to learn, to extend their reach. What might a million-year-old technological civilization know about what lies beyond the observable horizon? What might they have built? What might they understand about physics that we have not yet imagined? These are not idle questions. They are serious ones in the field of SETI, the search for extraterrestrial intelligence, and in the emerging field of what some researchers call technosignature detection, the search for physical signs of advanced technological activity in the cosmos. We have found no such signs. The sky, as far as our instruments can hear, is silent. This is known as the Fermi paradox, the apparent contradiction between the high probability of other technological civilizations existing, given the size of the universe, and the complete absence of any evidence for them. Scientists soon discovered that the Fermi paradox cuts differently depending on your cosmological framework. In a truly infinite universe, or in a multiverse with infinitely many observers, the absence of detected civilizations in our observable sphere could simply be a selection effect. If civilizations are common, but their signals are weak, or their technologies incomprehensible to us, or their motivations unlike ours, we might simply not recognize them, even if they were present. In a multiverse with different physical constants, intelligent life might be extraordinarily rare, possible only in universes with very specific parameters. Our universe might be one of the few, or one of the many. We don't know. In the many worlds, quantum branching, every civilization that has ever faced an existential choice, every moment where a small quantum fluctuation could have tipped the balance between survival and extinction, exists in both outcomes across the branching tree. In some branches, they survived. In others, they did not. In our branch, we are here. In our branch, the great silence remains. The answer raised an even bigger question, one that goes to the heart of the cosmic loneliness we sometimes feel when we contemplate the scale of the universe. Is this silence meaningful? Does it tell us something about the nature of intelligence in the cosmos, or the nature of consciousness, or the nature of civilizations? Or is it simply the result of distance, the vast, uncrossable distances between islands of complexity in a predominantly empty universe? We don't know. But the silence is interesting. It is the kind of silence that seems to be saying something, even though we haven't yet learned its language. And perhaps that is what makes the night sky so beautiful. It is a map of mysteries. Every point of light is a question. Every dark gap between the stars is a space where something unknown may be unfolding in silence, beyond our reach. Yet somehow, the scale of it all does not make us feel small, or rather, it makes us feel small and immense at the same time. Small in the physical sense, immense in the sense that we can hold this whole vision in our minds, turn it over, examine it. That capacity to contemplate infinity is itself one of the greatest mysteries in the observable universe. And yet, the mystery doesn't end with consciousness. Because we haven't yet looked at what science thinks the future of the observable universe holds, and how that changes the picture of what lies forever beyond our reach. Everything we have discussed so far has taken place across a timescale of billions of years. The Big Bang, 13.8 billion years ago. The first stars, igniting perhaps 200 million years after the beginning. The Milky Way, coalescing over billions of years. The solar system, forming 4.6 billion years ago. Life on Earth, emerging perhaps 3.8 billion years ago. You, here, now, listening. These numbers are large, but they are nothing compared to what comes next. The future of the universe. The deep future. The cosmological future stretches out in front of us on a scale so vast that the entire past history of the cosmos is barely a prologue, a single page at the beginning of a book that has no end. And in this deep future, the mystery of what lies beyond the observable horizon becomes even stranger. Because as time passes, the observable universe will not stay the same. It will shrink. Not shrink in the sense that space contracts. Space is still expanding. But shrink in the sense that the accelerating expansion will push more and more distant regions beyond our cosmic horizon, severing them from causal contact with us forever. The boundary of the observable universe is not fixed. It is closing inward, cosmologically speaking, in slow motion. Galaxies that are today at the edge of our observational range will, in the far future, cross the horizon and vanish. Their light will become redshifted into silence. Their signals will stop arriving. For all practical purposes, they will cease to exist within our universe. Let us walk forward in time, slowly, and see what the cosmos becomes. On a timescale of roughly 100 billion years, about 7 times the current age of the universe, the expansion of space will have carried most of the currently observable galaxies beyond the horizon. The local group, our own cluster of galaxies, including the Milky Way and the Andromeda Galaxy, will remain gravitationally bound, but the vast majority of what we see today will be gone forever. An observer in this era, looking out at the night sky, will see a cosmos that appears almost empty. The great cosmic web, the filaments and clusters and superclusters that dominate our current maps of the universe, will have retreated beyond any possibility of detection. They will not know those structures existed. They will look at the sky and see a small, isolated group of galaxies, their home, surrounded by apparent emptiness. They will have no way of knowing about the 2 trillion galaxies that once populated the observable universe of their distant ancestors. This thought is quietly devastating. Knowledge that exists today may be permanently inaccessible to future minds, not because of ignorance or lost archives, but because the universe itself will have moved the evidence beyond reach. Yet another mystery emerged in thinking about the far, deeper future. On a timescale of roughly 100 trillion years, 10,000 times the current age of the universe, the last stars will be burning out. Star formation will cease as the gas and dust that feeds it is exhausted. One by one, the lights will go out. The universe will enter what cosmologists call the degenerate era, an age of cooling embers. White dwarf stars, slowly radiating their heat into the void. Brown dwarfs, never quite massive enough to fuse hydrogen, drifting through the dark. The universe growing dimmer, colder, slower, with each passing eon. And then, even the white dwarfs will fade. On timescales of 10 to the power of 40 years, a number so enormous that no human intuition can process it. Even the protons that make up ordinary matter may decay, breaking down into lighter particles and radiation. The solid material of planets and dead stars will dissolve into a thin gas of electrons, positrons, and photons. The universe will become a vast, cold sea of black holes. The last gravitationally bound objects, consuming everything in their vicinity. And then, even the black holes will evaporate. Through a process predicted by Stephen Hawking, a slow quantum radiation of particles from the event horizon. Black holes gradually lose mass over time. The most massive black holes will take unimaginable timescales to evaporate. 10 to the power of 100 years and more. But eventually, even they will vanish. The final state of the universe is pure radiation. A thin, cold, featureless sea of photons and leptons, growing ever colder as the expansion continues, approaching but never quite reaching absolute zero. This end state is called the heat death of the universe, maximum entropy, minimum structure, not the productive uniformity of the early universe that gave rise to structure, but the dead uniformity of complete thermal equilibrium. And here is where the mystery of what lies beyond the horizon connects to the deep future in a remarkable way. Scientists soon discovered that this future is not certain. The accelerating expansion is driven by dark energy, and dark energy is something we don't understand. We don't know if it is constant, or if it changes over time, or if it might, at some point in the future, begin to behave differently. If dark energy increases in strength, the expansion could accelerate beyond anything our current models predict. In the most extreme version of this scenario, called the Big Rip, the expansion eventually becomes so rapid that it tears apart not just clusters of galaxies, but galaxies themselves, then solar systems, then planets, then subatomic particles, all of reality unraveling in a final, catastrophic expansion that destroys the distinction between structure and emptiness. If dark energy decreases, or if it changes sign and becomes attractive, the expansion could slow, stop, and reverse. The universe would begin to contract. Matter would crunch back toward itself, temperatures would rise, and the cosmos would collapse in a final cataclysmic event, sometimes called the Big Crunch. Some cosmologists speculate that a big crunch is not the end, but a transition, a bounce that gives rise to a new Big Bang, a new expansion, a new universe. This is the cyclic universe model, in which the cosmos oscillates endlessly through cycles of expansion and contraction, each one a new universe, each separated from the last by a moment of maximum compression. The answer raised an even bigger question. In such cyclic models, what came before our Big Bang? Was there a universe before ours? Did it collapse into the singularity that became our beginning? Does the cycle stretch backward as well as forward, through an infinite past as well as an infinite future? If so, then our universe is not just one of many in space, it is one of many in time. A single iteration in an endless cosmic breath, in and out, expanding and contracting forever. And what lies beyond our observable universe in this picture includes not just other regions of space, but other eras of time, past universes and future universes, separated from us not by distance but by the great barrier of maximum density that each collapse produces. These are the grandest structures in cosmology's imagination. And they raise the question that draws us toward the final chapter of this journey. What does all of this mean? Not scientifically, not mathematically, but for us, for our lives, for the way we stand under the night sky and look up. There are limits to what we can know. This is not a failure. It is not a shortcoming of science or a gap in human intelligence. It is a feature of the universe we inhabit, a feature as fundamental and as real as the speed of light or the expansion of space. The cosmic horizon is a knowledge horizon, a boundary beyond which empirical information cannot reach us. And the existence of this boundary has profound implications not just for cosmology, but for how we think about knowledge itself. Science is built on observation, on testing hypotheses against evidence, on the willingness to be wrong, to revise, to update beliefs in response to new data. This is its great strength. This is why it has produced the extraordinary map of reality we carry today. But the cosmic horizon reminds us that some questions may be genuinely beyond the reach of empirical investigation, not because we lack the technology, not because we haven't tried hard enough, but because the information we would need simply does not exist within our light cone. We can reason about what lies beyond the horizon. We can build mathematical models. We can look for indirect signatures, the circular imprints of bubble collisions on the CMB, the statistical patterns that might hint at a broader landscape. But we cannot observe it directly. We cannot send a probe there. We cannot receive a signal from it. And yet scientists soon discovered something remarkable. The existence of the horizon does not make the questions meaningless. It makes them deeper. In science, the questions we cannot answer often do more work than the ones we can. They mark the boundaries of our knowledge, yes, but they also tell us something about the shape of that knowledge, about what kind of universe produces beings who can ask questions they cannot answer, about the strange position we occupy as finite minds in what may be an infinite reality. The physicist David Deutsch has argued that explanatory knowledge, understanding the world through theories, through models, through mathematical frameworks, is fundamentally different from mere observation. A good theory does more than describe what we've seen. It reaches beyond the observable, makes predictions, reveals structure. In this sense, cosmologists studying what lies beyond the horizon are not abandoning science. They are practicing a deeper form of it, one that uses the full power of mathematical reasoning to follow the logic of known physics into regions that observations cannot directly reach. This is how physics discovered black holes before we observed one. This is how physics predicted the existence of the Higgs boson decades before the machinery to detect it was built. Theory, when it is correct, can see further than instruments. What does the theory see when it looks beyond our horizon? It sees a cosmos that is, in almost every version of the mathematics, vastly larger than what we observe. Whether you follow the implications of inflation, or the mathematics of a flat universe, or the framework of quantum many worlds, or the multiverse landscape of string theory, the answer that emerges again and again is the same. There is more, much more, almost certainly more than we can imagine. The answer raised an even bigger question, perhaps the most important question of all. What does it mean to live in such a universe? We are beings with finite lifetimes, finite minds, finite senses. We inhabit one planet around one star in one galaxy, in the observable sphere of one region of what may be an infinite cosmos. Our lives last decades. Our civilization has existed for a tiny fraction of the universe's age, and yet we know this. We have reasoned our way to this extraordinary picture. A cosmos so vast, so old, so complex, so full of mystery that every answer we find opens 100 new questions. There is something astonishing in this, not disorienting, astonishing, because the fact that we can know what we know, that mathematics developed by human minds can describe a universe 13.8 billion years old, that instruments we have built can detect the faint afterglow of a cosmic event before which time did not exist. This is not trivial. It is, perhaps, the most remarkable thing about the universe. Not that it is large, but that it is comprehensible. Einstein once remarked that the most incomprehensible thing about the universe is that it is comprehensible. Across the cosmic scales, the same equations apply, the same mathematics, the same physical laws. The universe, for reasons we don't fully understand, is legible to minds that arose within it. We can read part of the book, we can see partway through the library, and we can sense, even if we cannot see directly, that the library is immense. Scientists soon discovered, however, that there is a kind of peace in accepting the limits of what can be known. Not resignation, not defeat, but the particular peace that comes from understanding precisely where you stand, from holding the known and the unknown simultaneously, without the need to collapse one into the other. The cosmic horizon is not a wall we are pressing our faces against in frustration. It is a vast sphere we inhabit with gratitude, a sphere containing everything that human minds have ever seen, and every mystery we have ever explored. and every question that has ever made us look up at the sky with wonder. Beyond that sphere, something exists, something vast and perhaps infinite, something that may contain echoes of everything we know, or variations beyond our imagination, or entirely different mathematical structures that would be unrecognizable as reality to any mind shaped by our universe. We don't know, and that is a gift. Not knowing is not a problem to be solved. It is the permanent condition of finite minds in an infinite cosmos. It is the horizon that walks ahead of us, no matter how far we travel. It is the thing that makes the journey worth taking. The silence beyond the observable universe is not empty. It is full of what we have not yet imagined, full of what no language we have yet invented can describe, full of questions that have not yet been asked by anyone who exists within our cosmic horizon. And somewhere out there, in the flat, vast, continuing expanse of a universe larger than our minds can process, there may be another mind, in another moment, looking up at their own horizon and wondering what lies beyond it. Their sky is different from ours, their universe is their own. But the question is the same. The question has always been the same. What is out there? We are back, now. Still here, still floating in the dark, with the stars above and below, and in every direction. The journey has been long. We have traveled farther, in imagination, than any body could follow, past the edge of the observable universe, through the inflationary foam, into landscapes of mathematics that may or may not be reality, across the branching tree of quantum possibilities, forward into the deep future, where the stars go cold. And now we return to this moment, this breath, this quiet. Let it settle. There is a particular feeling that comes at the end of a journey like this. It is not excitement, exactly. Not fear, not even wonder, in the sharp, sudden sense of that word. It is something slower and softer, something that accumulates over the course of a long contemplation of large things. The feeling is this, that you are small, and that being small is not a diminishment. It is a location, a particular, irreplaceable point in the vast structure of space and time and possibility from which the rest of the universe can be observed and felt and thought about. You are here, right now, in this body, on this planet, under this sky. The observable universe extends 46 billion light years in every direction around you. You are at its center, not because the universe revolves around you, but because every observer is at the center of their own cosmic sphere. This is a gift of physics. Every mind is the center of its own sky, and beyond that sky, something extends. We do not know exactly what. We may never know exactly what, but we know enough to say, with confidence, it is large. It is real. It is governed by the same elegant mathematics that governs the atoms in your body and the stars in the sky above you. The universe is not indifferent to your existence. The universe is not aware of your existence. But the universe, through a chain of events stretching back 13.8 billion years, through the quantum rolls and gravitational collapses and stellar explosions and planetary chemistry that preceded you by eons. The universe produced your existence. You are not a stranger here. You are made of the same atoms forged in ancient stars that went supernova billions of years before the Earth existed. The iron in your blood was born in stellar cores. The calcium in your bones was scattered by the same supernovae that seeded the molecular cloud from which the solar system formed. The carbon in your cells traces back to nuclear reactions in dying stars that will never be seen again. You are, in the most literal and profound sense, made of the universe. You are the universe arranged into a shape that thinks and wonders and asks what lies beyond. That is not nothing. That is, perhaps, the most extraordinary thing about a 13.8 billion-year-old cosmos that has been for most of its history dark and cold and indifferent. It became curious. The quietest and most astonishing fact in all of cosmology is not the number of galaxies, or the age of the universe, or the scale of what lies beyond the horizon. It is this: in at least one place, in at least one arrangement of matter, perhaps in many, perhaps in infinitely many, the universe has folded back on itself and asked what it is. We are that folding, that asking, and what we have found in asking what science has revealed across centuries of careful, patient, luminous effort is a cosmos of extraordinary beauty, not the beauty of decoration, the beauty of depth, the beauty of a thing that rewards attention, that gives more of itself the more carefully you look, that opens into vistas of wonder every time you think you have reached a wall. The horizon is not the end. It is a reminder that the story continues past what we can read, that the universe is larger than any mind, larger than any library, larger than any language we have built. And that is, perhaps, what we came here to feel, not to have answers, but to feel the rightness of the questions. There is a practice that astronomers sometimes describe, the practice of going outside on a clear night and simply looking, not searching for anything specific, not trying to identify constellations or calculate distances, just looking, letting the scale of it arrive in your body, not just your mind. The light that touches your eyes on a clear night has traveled distances so great that it left its source before the Earth existed. Some of those photons began their journey when the Milky Way was still forming. Some of them come from galaxies so remote that the stars which emitted them have long since died. And the light is all that remains of their existence, a ghost, traveling through the expanding universe for billions of years, arriving at this moment, at these eyes. What lies beyond the observable universe is the continuation of all of this. The same light, still traveling in regions we will never observe. The same stars, burning in galaxies no telescope will ever find. The same darkness between them, deep, silent, vast. The darkness that is not absence, but the space between things. The pause between notes, the medium through which all of this extraordinary complexity propagates. Whatever else is out there, whether it is more of the same, or inflationary foam, or other bubbles, or mathematical structures entirely alien to ours. It is part of the same whole, part of the same cosmos that produced you, and the night sky above you. And the question you are carrying right now, that question connects you to everything. To the astronomers who mapped the CMB and found the seeds of all cosmic structure. To the physicists who followed the equations into territories beyond observation. To the ancient humans who looked up at the same stars and felt the same incomprehensible immensity pressing gently against the edges of their understanding. We are all looking at the same horizon. We are all wondering what lies beyond it. And we are all, every one of us, part of the universe that produced the wondering. So let the question stay with you tonight. Not as a burden, as a companion. Let the scale of it hold you rather than overwhelm you. Let the not knowing be a kind of home, a spacious, quiet place where curiosity lives and rests, and occasionally, when the night is clear and the mind is still, opens its eyes and looks up. The universe is large. You are here. Both of these things are true. Both of them are extraordinary. And somewhere, beyond the edge of everything you can see, something continues. It always continues. Rest well.